Okay, so here we're told we have this prism and we want to know what the area of the base is, and we're told, I didn't post it here, but that the area of each of the squares, right, on top of the prism right here is 1 square unit. So let's say it's 1 foot squared, 1 inch squared, we don't know. So it's one, let's say, unit squared, or a square unit. Okay, so what is the area of the base and how do we sketch it? Well, if you can imagine what this is, right, this is the top of the shape as we're seeing it, right? These shapes right here. But if you look at the way the shape is set up, you can also imagine that the exact same thing must be happening here on the bottom. So really we're just sketching this out. If you think about what we have 1, 2, 3 squares, and then 2 squares, and then 1 square. So we can set that up quickly. We can do a rough sketch here, right? So if we have 3 squares, I'll start with the largest first, and they should all be the same size. If you have graph paper, I already used that. It's nice and easy there. And then 2 squares, and then 1 square. So this is essentially what you have here for the base. And what is the area? Well, whatever the unit represents, we have 1, 2, 3, 4, 5, 6 squares. So it's 6 square units, right? Or 6 units squared. So those are identical. You could write 6 units, right, squared. Okay, so now we have that set up, and here in the second part, we're told that the student here, Rashid, is trying to draw a net, which is a flat layout that will fold up to form the staircase prism. So we're flattening out the staircase almost as if it's a large piece of cardboard, so that when we fold it up, what we get is this three-dimensional staircase. That's the idea of a net. So here's the start of his drawing. We want to finish the drawing and give the surface area of the entire staircase. Okay, so here we have a start of the drawing. We have the left and rear sides, and what that's going to represent is here your left, and here in the back the rear side, right? The left is just this square, right, over here. Draw it. And the back is another square right there. If you can imagine seeing through this prism, that's what you would see. And then what's going to happen? Well, here we have our almost exact sketch of the top of the prism or the base. So we know we'll have to repeat that down here, right? So to set this sketch up, right, we've got 3 equal squares down here. Hopefully you have graph paper for this. And then 2 equal squares, and then 1 equal square. So now we have the top and the bottom, the left and the right, but now we need the actual stairs themselves, right? So we need this surface right here, right? The tops of the 1, 2, 3 stairs, and then these sides right here, 1, 2, and 3. So if we count that, it's 1, 2, 3, 4, 5, 6 rectangles that would fold up to complete the staircase. I'm going to imagine that this side would be, just a different color. This side, the top side, would be folded down to form this top up here. The bottom side would be folded up to form the bottom. And then you can imagine a crease right here. Right? If this crease is right here and you're folding this down and this up, the rear and left pieces do come towards each other. Right? You fold them almost together in a sense. But the rear one, you're not really going to fold it much. In fact, you can imagine, I guess, maybe it's easy to imagine that the rear is staying still, but the left is being folded up out towards you, right? So this is coming down, this is coming up, and this is going to the left. And essentially you're done. You just need to have another cardboard piece that'll cover these yellow sections right here. So what I'm going to do is imagine that all of those rectangles are equal, right, on the staircase. We don't know that, but we can assume it. If it wasn't equal, the rectangles would be different as we go through. But we're going to assume they're equal. That'll help us calculate. So how many rectangles do we need? Well, we have 1, 2, 3, 4, 5, 6 rectangles. So we set those up. 2, 3, 4, 5, and 6 rectangles. Pretending, of course, they're all even. Now this one will be folded up to form the actual stairs that we walk on. So we want to know the surface area of this thing. And we're going to use a little bit of inference here. I mean, here, if this is, right, a square, this left piece, which we can assume that it is, I guess, for the sake of this problem. Well, how long is it on each side? Well, 1, 2, 3 squares, right, form the length of this side, just as it does up here. So it's 3 feet, let's say, or 3 units wide. Now, it stands to reason that since this piece folds down and covers, right, and covers the rear, let's say, of the rectangle exactly, this side right here, that should also be 3 as well, right? So that's 3 as well. Now what about the height? How can we infer what that is? Well, I guess we're not told enough to really do it. We're going to assume that it is a square. So if it's 3 this way, it's also 3 in height. I feel like we should be told that. But once we know that, now we know we have 2 squares, each with area 9. So the left panel, we'll write these out. All right, that has an area of 9 units squared, or 9 square units, and that equals what we have in the rear panel. Right, the rear also has 9 square units. A little square sign there. Now here, we know the top and bottom each, as we said before, we have 6 square units. So the top has 6 units squared, right? And the bottom is equal, so that too has 6 units squared. And now what's left of these rectangles? And the rectangles must match the height that we set up so far, right? So they'll each be 3 tall, right? 3 squares tall. And since they are, this makes a little sense, I think, because if they're each 3 tall, right, how wide are they? Well, if you look at the formation of the rectangle, it matches, right, the square right there. So this side fits with that side right there, which means that if it matches the square, and the square is 1 square unit, that means they're all 1 by 1. So these are each 1 wide. So they're each 1 by 3. So 3 squares exactly fit into each rectangle. And what's that? Well, 3, 6, 9, 12, 15, 18. So the stairs themselves, right, the actual planks we're walking on, that's 18 square units. So now we sum these up, right? Well, 9, 18, 12 more is 30, and 18 more is 48. So you have 48 square units. Alright, so the last part of this problem, we're doubling the amount of stairs. We're having 6 stairs instead of 3, and we want to know how does this affect the surface area. So if we set up a rough sketch based on the net we have so far, right, if we look at the stairs, let's just do that first. We have 1 step, then 2, then 3. What's happening with each step is that we have, right, more surface area than before. So that kind of gives it away, I think, that if we double the amount of steps, you can see it right here, right, that's one other step, and another, right, and one more. Sorry, it's a little uneven. Oh boy. These should all be equal, sorry about that. But what's happening is what? Well, in this first row right here, we have 1 step, or surface area of 1. Then we have a surface area of 2, then a surface area of 3. So when we add the third row, we had 3 steps, which is 1 more than when we added the second row. This row is even more, 4, and then 5 steps, and then 6. So just the top area, originally it was 6. Now what is it? Well, 6 plus 1 is 7, 5 plus 2 is 7, and 4 plus 3 is 7. So what is that? Well, 7 times 3, this has an area of 21 square units. Right, so we add these up, plus. So what happened was we went from 6 to 21, just in this top section. And that's way more than double. Double would be 12 units. Here we have 21. It's over 3 times greater. And that's, again, because each row of, each step we add requires more squares to form the step. So now we have this piece, the left piece, is now what? Well, it's 6 by 3, right? 6 this way and 3 that way. It's a rectangle. And then the rear will be the same. It's another 6 by 3. And then down here we have, I can't fit it on the screen anymore, I ran out of room, but you can imagine it's going to be an exact copy of the one that we just drew up top, right? There's 4, and then, sorry, I ran out of room, 5 would go right off, and then 6. Right, so now you have this new net, and what's that? Well, it's 21 down here. So now these both have an area of 21, top and bottom. Now we need the rectangles that will fold over to form the steps. And they'll still be a height of 3. If you imagine this piece coming down and this one coming up, they form this narrow gap, which can be filled by these rectangles. Except now, how many do we need? Well, you can think about the steps, right, that are going to form here. And you'll have one here, one there, that's 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So this time we have these 12 rectangles, right? 2, 3, 4, 5, and then 6. So there's 6 here, just like before. But then I put dot, dot, dot. You want to draw this out as a net. There are 12 rectangles across, each with a height of 3. So what's that? Well, that's 36 right there. Plus 21 times 2, the base and the top, plus 18 times 2, right? That's the left and the rear panels. So we have 36, 42, and 36. Adding them up, 36 twice is what? Well, it's 72. Plus 42, and what do we have? Well, 70 and 40 is 110, plus 2 is 114 square units here. So it's more than double, because before we had 48 units, double would be 96, except we have 114. So clearly, and this is a pattern worth exploring, maybe we'll come back to in other videos, how would you predict future staircases for any given number of steps? It's kind of a fun question. But here what's happening is we're realizing, oh, this is certainly going to do more than double, right? When we double the number of steps, there's more going on here. That's really an important thing to realize. All right, thanks.